Hello again and welcome to Advanced Higher Physics Lesson 2, or more precisely Advanced Higher Physics Lesson 2A. I've decided to split up Lesson 2 into two parts, mainly because there's a new concept that we have to look at in this first part of the Lesson 2A that you won't have covered before in maths. It's something you will cover at Advanced Higher Math, but as you won't have started that course yet, it's something that I need to explain to you. So 2A, we're going to be looking at the concept that acceleration is something called the second differential of displacement with time. So, at this point, I think I have to be honest and have to say that this first part of the course is a bit like the first part of the higher course. It's mathematically quite rigorous. All the maths is basically front-loaded. Doesn't mean to say we're not going to use math later on, obviously we are, but I think the hardest bit of the maths is definitely right back at the beginning here. Okay, so what are we looking at here? Well, let's go back to what we did last time. Just a quick recap. So we've got a displacement time graph here, showing how the displacement of an object varies with time. Now you note I'm not really doing these graphs in straight lines anymore because we don't need to. This displacement time graph has a gradient. The gradient might be changing, but at every point it has a gradient. The gradient there is the rate of change of displacement with time. And the gradient of a displacement time graph we call the velocity. But the way that we write it down is we write it down ds by dt, because the velocity is the rate of change of displacement with time. What that means in the real world is how rapidly is displacement increasing as we move along here. So as we move along in this direction, how rapidly is displacement going up? So if you think of it in sort of terms of two bits here, as we move in this direction, how quickly is displacement going up here? And that's really all this is telling you. It's the gradient of the graph. So our equation here, v equals ds by dt, tells us the rate of change of displacement with time. Again, from before, we have a velocity time graph. And in this case, we could do either a straight line or we could do a wiggly line at the moment. We're not too bothered. But at any point in this graph, the gradient here is going to give you the acceleration. So the gradient would be a tangent to the line at that point. But the gradient is simply the rate of change of velocity with time. And we can write that underneath as A equals dv by dt. That's what we looked at last time. Now what we're going to do here is we're going to do a little bit of a technique where we're going to kind of combine these two together. So we're going to start off with A equals dv by dt, and we're going to take v equals ds by dt. So just the two equations that we had before. Now, another way of kind of writing this is that the acceleration, I'm really just actually changing the notation just to make it a little bit easier to understand. There's actually no change in what I'm writing. This is basically the differential with respect to time of the velocity here. Now remember that if the velocity up here is ds by dt, we can put that ds by dt into here instead of v, because that's basically the same thing. So what we can do is we can write this as A equals, it's the differential with respect to time of velocity, which is the differential of s with respect to time. Now, it doesn't kind of multiply up like letters. It's not quite algebra, but when you put these two together, this is called the second differential with respect to time. So basically we're differentiating s, the displacement with respect to time, and then we're going to differentiate it again with respect to time. And that will give us the acceleration. The way that we write that in maths, and again, if you do advanced higher maths, you will come across this, called the second derivative, is we write it as d2s by dt, well, I always call it dt squared. But basically, it's the second differential with respect to time. So we're differentiating something, and then we're differentiating again, and we end up with this function here. It looks complicated, but really it's just doubly differentiating. Okay, so we've got this far. Now, I've put a link in this post to a bit in the Khan Academy that tells you a little bit more about second differentials. And as I say, you will do it again if you do advanced higher math, but if you can understand it up to this point, that would be great. If you don't, then I can put up more links to help you. So at this stage, we've got the second differential of displacement with respect to time is the acceleration. So this is like the rate of change of, or the rate of change of the rate of change of displacement. And I'm going to try and explain that a little bit in a slightly different way on the next sheet. Okay, so I'm going to go back to this graph here, the displacement time graph. So this could be for a journey, and the displacement is increasing at an increasing rate, I suppose, over the journey. And as we've said a few times before, if we get the gradient to that point there, this is actually the rate of change of displacement with time. It's the velocity, but it's the rate of change of displacement with time. If we look at the gradient at different points in this graph, what we can see is that the gradient is definitely increasing. Or to put another way, ds by dt is definitely increasing as we move along the time axis. So as we move along in this way, ds by dt is getting bigger. The gradient is getting steeper, the gradient is getting a larger number. So if we then take this across to a graph here, and we've done this graph before a lot of times, but instead of labeling as velocity, because the gradient here is the velocity, but instead of labeling it as a velocity, I'm going to label it as ds by dt again. And we're going to have time down there. Now, ds by dt, the gradient here, this is basically a gradient time graph. The gradient is increasing as time goes on as well. So if I draw the graph like this, then the gradient's going to be increasing too. There's a constant increase, well, it could be a constant increase, or in this case I've made it a slight curve, but there's an increase in the gradient over time. And this is the velocity here. Right, we're not going to worry too much about that, but this is actually the velocity too. So again, a way we can look at this is that as time goes on, the rate of change of ds by dt with respect to time, so the rate of change at this particular point here, say, of ds by dt with respect to t can be written as the gradient of this graph here. So the gradient of the graph at this point is an idea of how quickly, how rapidly, can't really use these words, but how rapidly ds by dt is increasing with time. Right? We do have to use the words rate of change though. So that's basically saying how rapidly is ds by dt changing with respect to time. So d of ds by dt. I know it sounds complicated, but just bear with me. And that can be written as d2s by dt squared, or it can be written as the rate of change in velocity, because that's velocity there, over time, by time, and it can also be written as the acceleration. And that's kind of tying us right back in with almost down to National 4 physics, because the rate of change of velocity with time, the increase in velocity every second, is the acceleration. The difference here is that we are using a bit of differentiation. We're using a bit of calculus that will become clear very later on why we're doing this. We're using a bit of calculus to show you that actually, if you know something about the displacement right back at the very beginning, then you can actually go directly to the acceleration. Okay, So that's that so far. Now, I'm going to put up a bit on the Khan Academy again that will explain a little bit about this formation down here. And I can put up some other videos that will explain how this works in a slightly different way. What I want to think about though is, well, okay, we've got that so far, but what does this actually mean in the real world? Well, in the real world, what's actually happening in this graph here is that the rate of change, the increase in displacement in every second that you're moving forward is actually increasing. So every second that you move forward, the displacement increases by a different amount, by an increasing amount. So this becomes, say, 2 meters for the first one, for the first second. In the second second, it might be 3 meters. The person's displacement has increased by more in the second second than it has in the first second. Then the next second, the displacement has increased by a total of maybe another 4 meters. So every second that we move forward here, the displacement is increasing by a greater amount. Now what that actually means, the reason that's happening is because the velocity is changing too, but we're going to come back to that afterwards. If we then look at what's happening in terms of the velocity, well, the velocity, the person starts off at a low speed and then they end up going at a higher speed or higher velocity, and then they end up going at a much higher velocity. So at this point they're going at 2 meters per second, at this point they're going at 3 meters per second, and at this point they're going at 4 meters per second. So their velocity is increasing. But remember, the velocity is actually the rate of change of displacement. So displacement is increasing at a greater rate every second that you move forward, and the velocity is therefore increasing at a greater rate. So ds by dt is actually increasing, and if we look at then the rate of increase of ds by dt, which is basically the velocity, the rate of increase of the velocity, then that gives us an acceleration. So because the velocity here is increasing too, remember this velocity is effectively ds by dt, then it means that the acceleration is going up too. Okay, so the acceleration, which is dv by dt, is given by the rate of increase of the velocity, which is ds by dt. I know there's a lot there to get your head around, but try to do it and it might make things a bit easier. It does take a while though. I do appreciate that. Right, I'm going to leave this at that for the moment, and I think that'll do us. The main thing you have to get out of this lesson is that the acceleration can be written as dv by dt, but it can also be written as d2s by dt squared. Okay, thank you.